Hello, in this video we're going to see some representations of graphs. So the usual computer representation of graph involve one of two data structures, either an adjacency list or adjacency matrix. So suppose a graph has a node. So for example, this one has 4 nodes. This numbering imposes an arbitrary ordering on the set of nodes. Recall that a set of an ordered collection. Having ordered the node, we can form some n by n matrix where entry ij is the number of arcs between the nodes. So ni and nj. This matrix is called adjacency matrix A of the graph with respect to this ordering. So that's aij equal p, where there are p arcs between ni and j. So here is an example. I have directed graph, so 4 nodes. So I have node 1, 2, 3, 4. 1, 2, 3, 4. So I have 4 by 4 matrix. So do I have a connection between 1 and 1? There is a loop, so that's why you put 1. How about between 1 and 2? Yes. 1 and 3, there isn't, so we put 0. Between 1 and 4, there isn't, we put 0. And then how about from 2 to 1? There isn't. So since it is directed graph, then we don't have connection between 2 and 1, just 1 to 2, but not 2 to 1. So therefore you have a 0 here. How about from 2 to 2? No loop. 2 to 3, yes, so therefore you have a 1. 2 to 4, yes. And so on. 4 to 1, you check. 3 to 1, no. And 3 to 2, yes. And 3 to 4, no. And 3 to 3, no. So both of them 0 here. The same with the 4, you check where 4 is connected. 4 is going to 3 only, so that's why you have only 1 here. Everything else is a 0. You have 2 to 4, but you don't have 4 to 2, because it's directed graph. If the graph is not directed, then it's different. So let's do this example. You can stop the video and try this one here. So I have 5 nodes, so that means 5 by 5 matrix. So what we're gonna see, 1 to 1, yeah, there is a connection, you put a 1. But 1 to 2, yes. 1 to 3, no. 1 to 4, no. And 1 to 5, I have 2 arcs, and therefore I put a 2. 2 to 1, yes. 2 to 2, we have a loop. 2 to 3, 2 to 4, 2 to 5. And 3, so I have 3 connected with the 2 and the 4, with the 2 and the 4. Everything else is 0. For 4, I have connection between 2 and 3. 2 and 3. Everything else is 0. And for the 5, I have 5 to 1. I have 2 connections for 5 to 1. And then 5 to 2. I have 1. And nothing else. 0, 0. So let's see this example. Now the matrix is given, and the question is, draw the graph. So this is node 1, 2, 3. 1, 2, 3. So let me draw 1, 2, and 3. So it looks like 1 to 1 we don't have no loop, but 1 to 2 we have 2 arcs. 1 to 3, nothing. 2 to 1 we have 2 arcs. 2 to 2, nothing. And 2 to 3 is 2 arcs. And then 3 to 1, nothing. 3 to 2, 2 arcs. And 3 to 3, nothing. So it could be this way, or you could draw it like this. 1, 2, 3. So it doesn't matter. How about this one here? So let's see, we have 1, 2, 3, 4, 5. We have 5 nodes. So I have 1 to 2. 1 to 4, 1 to 3, and 2 to 1 we already have. 2 to 5, that's good, that's it. And then go to 3, we have 3, 1, and 3, 5. 3, 1, we already have. 3, 5. And then 4, 1, and 4, 5. 4 to 1, and 4 to 5. And what else we have? 5 to 2, 3, and 4, which you already have, and here is the graph. And of course you could draw it differently than this one, maybe. Depends on what's the position you have for the node. So maybe I have this. Could be that you draw it this way. 1, 2, 3, 4, and then 5. So it could be this way. So the other example of storing graphs will be a list. And why is a list better? Because sometimes you have a lot of nulls, a lot of zeros, no entries, like all of this. So it's taking space. So you need n by n storage. So, and also these zeros here. So if the graph doesn't have a lot of connections, it's better from a storage point of view. It's better to have a list, store it as a list. Let's see an example here. So many graphs, far from being complete graphs, have relatively few arcs, such graphs have sparse adjacency matrices. That is, the adjacency matrices contain many zeros. Yet, if the graph has a node, it still requires n squared data items to represent the adjacency matrix, even if many of these items are zero. Any algorithm or procedure in which every arc in the graph must be examined require looking at all n squared items in the matrix. So can you imagine if n, you have a million of data? So then the runtime for your algorithm to search this matrix will take n squared, which is a long time. So therefore, storing the data as a list, linked list basically, is more efficient. Even though the storage nowadays is relatively cheap, but what matters is the time, how long it takes to search this matrix, and therefore we use a list instead. So let's see an example here. Here I have this graph. So as you see, these are the nodes 1, 2, 3, 4. And if you took any Java, you've seen a list, an array, so it's linked. So you have 1 is connected to 1, and connected to 2, and connected to 3. So the order here 1, 2, 3, 4. 1, 2, 4, it doesn't matter. So you could start with the 3 here and then 1 here. And this is the null pointer. That means I'm not pointing to anything else. That's it, we're done. So you could have a linear search like this. What is 1 connected with? And it's easy. You could see 1, 2, and 4. And so let's draw adjacency list represented for the indicated graph, like the graph we've seen before. So take a moment and draw the list. So we have 5 nodes, 1, 2, 3, 4, 5. So 1 is connected with 1 and a 2 and a 5 twice. And a 2 is connected with the 2, 3, 4, 5, and 1, and then null pointer. So as I mentioned, the order does not matter. So 3 is connected with 2 and 4. 4 is connected with 2 and 3. And 5 is connected with 1 twice, and then 2. Here is the last example here. The list is represented. We need to draw the graph that represents this list. So 1 is connected with the 2 and 3. 2 is connected with 1, 3, 4, and 4 again. So here 2 4s. 3 connected with the 1, 2, with 3, that means there is a loop, and with 4. And 4 is connected with 2, 2 again, and then 3. And this is the graph that represents this adjacency list. I hope this video is helpful.